Welcome everyone. Today I will present our work, CoST, Efficient Collaborative Perception from Unified Spatiotemporal Perspective. This is a joint work by researchers from Hangzhou International Innovation Institute, Beihang University, and University of California, Los Angeles. Our goal is to improve collaborative perception in autonomous driving using a unified spatiotemporal approach. Autonomous driving requires accurate perception, but a single vehicle often suffers from occlusion and limited sensing range. Collaborative perception allows multiple agents to share complementary information, improving the overall perception. However, prior methods separate multi-agent fusion and multi-time fusion into two steps. They do not address communication and fusion from a unified spatiotemporal perspective, which limits their effectiveness. We propose two core ideas. First, space-time transmission. We reuse static data and only transmit dynamic features, which significantly reduces communication bandwidth. Second, unifying space-time convergence. We model historical subjects as delayed copies of current subjects, enabling cross-temporal and spatial information fusion in a unified manner. This slide shows our overall framework. We begin with V2X metadata sharing, followed by feature extraction. In ST transmission, static objects only require one observation record, saving bandwidth. Finally, unified ST fusion aggregates all features to produce a more comprehensive prediction, improving perception in complex scenarios. The goal here is to transmit only dynamic object features while ensuring scene completeness. We first generate a saliency map to identify important regions. Then we compare current and historical saliency maps to locate dynamic regions. Next, we create a selection mask to filter which features to transmit. Finally, the receiver reconstructs the complete feature map using transmitted dynamics plus stored static features. Our second key module breaks the barrier between spatial fusion and temporal fusion. We treat agents at historical time steps as current agents with delays. We project historical features to the current frame, allowing them to act as additional agents for fusion. We also adopt a recurrent modeling strategy to reduce computational cost while preserving long-term context. This module efficiently aggregates cross-agent features while reducing computation. We inject agent-specific meta-information, such as speed, latency, or infrastructure markers, to optimize feature alignment. Using deformable attention, we only sample a small number of key regions per query point, avoiding the high cost of full attention. We evaluate our approach on three datasets: V2V4 Real for real-world V2V communication, V2Xset for V2V and V2I interaction data with simulated noise, DIR V2X for real-world V2I communication. We compare different fusion strategies and measure LiDAR-based vehicle detection performance using AP at 0.5 and 0.7 across different distance ranges. This table summarizes the performance of different methods on all three datasets. Our method CoST achieves the highest AP across almost all settings, demonstrating its superior accuracy. This highlights the benefit of our unified spatiotemporal approach compared to both early and late fusion baselines. This figure shows the trade-off between bandwidth and accuracy. Our method CoST achieves the best performance while using significantly less communication bandwidth compared to other methods. This validates the efficiency of our spatiotemporal transmission mechanism. First, the ablation study, top table, shows the impact of adding each component, spatial features, align transformation, AT, and temporal features on detection performance. We can see that by progressively adding AT and temporal modeling, the AP at 0.5 and AP at 0.7 increase, achieving the best performance with all modules enabled. The computational efficiency, bottom table, compares our CoST framework with other baselines. CoST achieves the highest accuracy while maintaining a competitive inference speed and relatively low parameter count compared to V2X VIT and CoB EVT. This demonstrates that CoST is both effective and efficient. This slide shows visual comparisons of detection results on real-world LiDAR data across different methods: OPV2V, CoB EVT, V2X VIT, and our CoST. Each colored box represents detected objects: green for ground truth, red and orange for predictions. We can see that CoST captures more objects and provides more accurate localization, especially in complex and cluttered scenes, compared to the other baselines. This qualitative evidence further supports the quantitative gains shown in previous slides. Core contributions. We propose the CoST framework, which constructs a unified spatiotemporal space by treating historical agents as time-delayed copies, reducing redundancy and improving accuracy. We designed the STT module to realize selective transmission of dynamic features, and the USTF module to unify spatiotemporal fusion, solving the pain points of traditional methods. We developed the MODA module and recurrent modeling strategy to balance perception accuracy and computational/bandwidth costs. We verify the superiority of our framework on 3 datasets, demonstrating improved accuracy and reduced bandwidth usage. Future directions. We plan to extend CoST to multimodal perception, combining images, radars, and LiDAR data to further improve scene adaptability. We aim to optimize for long delay scenarios, designing more robust spatiotemporal alignment strategies for delays exceeding 500 milliseconds. Finally, we plan to implement real-world deployment, adapting to complex interference and dynamic topologies in real V2X communication environments.